Welcome to this presentation. My name is Vegard, and in this VHDL presentation I will be talking about regular sequential circuits and its basic concepts. First of all, I would like to explain shortly what sequential circuits means, so hopefully it will be easier to understand when I go a little deeper into the different types of sequential circuits. Basically, sequential circuit is a logical circuit that depends on both the present value of its input signals and on the past history of its inputs. The sequential circuit's outputs can depend on past history inputs because it has a built-in memory. This makes us able to reuse the output into a different input if needed. After you have watched this video, you will be able to differentiate between regular sequential circuits, FSM and FSMD. You will also be able to write a VHDL description for the basic building blocks used in regular sequential circuits. Sequential circuits can be categorized into three different categories, depending on the next state logic. We have a regular sequential circuit, we have FSM, which is finite state machine, and we have FSMD, which is finite state machine with a data path. I will now talk about the differences. The regular sequential circuit. The next transitions in the circuit exhibit a regular pattern, as in a counter or shift register. The next state logic is constructed primarily by a pre-designed regular component, such as an incrementer or shifter. As we can see on this picture I have taken with me, we can pretend this is a counter which increments from S0 to S1, from S1 to S2, from S2 to S3, and from S3 to S0. As you can see, it has a very basic structure. It is not dependent on even time and other inputs. A finite state machine is one circuit that has limited or finite number of possible states. In general, a state machine is any device that stores the status or something at a given time and can operate on input to change the status and an action or output to take place for any given change. We can take example in a computer. A computer is basically a state machine, and each machine instruction is an input that changes one or more states and may cause other actions to take place. Here I have drawn a picture that will hopefully make you understand a little clearer. This has three states, green, red and yellow, and as you can see they are all affected by the time and that they only go certain ways. As you can see, green cannot go back to red, it has to go through yellow first. But if we start in the green state, you can see that it has to be in the green state until the time is 1. When the time is 1, it goes further away to the yellow, and when it's there for 1 second, it goes to red, and it's staying in red for 1 second before it goes back to the green. So as you can see, this final state machine is dependent on the outputs of the last state and on the time. Now I'll talk a little about the FSMD. An FSMD combines a controller modeled as a finite state machine and a data path. The data path receives commands from the controller and performs operation as a result of executing those commands. A data path contains the components of a digital system that perform numerical computations of the system. The circuit consists of a regular sequential circuit and an FSM. The two parts are known as a data path and a control path, and the complete circuit is known as an FSMD. This type of circuit is used to implement an algorithm represented by the register transfer methodology, which describes system operation by a sequence of data transfers and manipulations among registers. The job of the finite state machine is to sequence operations on a data path. Here I have shown, as I just told, that the finite state machine tries to sequence operations on a data path, and the data path is tries to perform numerical computation for the system. So these two has to cooperate in a good way. Now I will go through the code of a basic D flip-flop with an asynchronous reset. As you can see on the truth table on the right side, this shows us that the output Q will retain the value as long as the reset is set to low. When the reset is set to high, 1, the output will be reset to 0. Also, the truth table shows us that when there is a rise in the clock signal, the output will be set to the same as the input, that is the D. Let me quick go through the code with you. First off, we start with defining the inputs and outputs. D, clock and reset is regular standard logic inputs, and Q is the only output we have that is also a regular standard logic. In the architecture, we use a process containing both clock and reset, because both of these is going to affect the inputs and outputs, depending on their high or low state. The process checks if the reset is 1. If the reset is 1, the Q will be reset down to 0. Else if there has been a rising edge, meaning the clock is 1, the Q will be given the value of D. That was everything I was going to go through today. If you have any questions, please feel free to leave a comment, and we will respond as quickly as possible. Thank you very much for listening.